Alright, so we are looking at rates of change, and here we have the problem that there are two planes heading towards an airport. One plane is heading west at a speed of 120 miles per hour, while the other is heading north at 150 miles per hour. What we want to know is what is the rate at which the distance between the planes, that should be planes, changing when the westbound plane is 180 miles from the airport and the northbound plane is 125 miles away. So the first thing we're going to do in any of these word problems, or any word problem we get, is draw a picture. So here is my airport. So we're going to have a plane that is heading north, so it's going to be coming up like this. We're going to have one that's heading west, so it's going to be coming from this direction heading here. What we want to know is how the distance here between the planes is changing. Alright, so really quick, I'm just going to label these. I'm going to label this distance of the northbound plane. I'm going to label this, I don't know, let's call it y of t. So that's going to be its distance at time t. This one we'll call it x of t. So that'll be the westbound plane. Distance at time t. And the distance between the planes, let's call that z. So we'll call that z of t. So the distance between the two planes at time z. Remember, if you want to make this easier, you can just call them x, y, and z. I kind of like to include the t so I remember that they're functions. Now, what we're looking at is we're looking at the time in when the westbound plane is 180 miles away. So this is equals 180. The northbound plane is 225 miles away. Okay, great. And this distance we can figure out by using the Pythagorean theorem. So if we use the Pythagorean theorem, it's going to be, I'll do it in a different color and we'll do it right down here. It's going to be, well, y of t squared plus x of t squared equals z of t squared. So that's going to be 225 squared plus 180 squared equals, I'm just going to go ahead and call that z squared. So if I add these two together, and then I take the square root, what I get is that z is going to be approximately 288.14. So let's write that down. 288.14. Okay. And let's go ahead and write down some of the other information we have. So I know that the plane heading west, is going at a rate of 120 miles per hour. That means that this distance, x of t, is changing at a rate of 120 miles per hour. So let's go ahead and write that down. So I know, well, another way to write rate of change, that's just the derivative. So x prime of t is going to equal 120 miles per hour. Okay, and then I know the north plane, so that plane heading north, is going at 150 miles per hour. So that means that this distance y is changing at a rate of 150. So remember, rate of change is the derivative, so y prime of t equals 150 miles per hour. Now, remember, we're not just interested in the speed, we're interested in the velocity. So remember the derivative is velocity. So, what's their velocity? Is it positive or is it negative? Well, since this distance is becoming smaller because they're heading towards this airport, so since the distance is becoming smaller and we're losing distance, both of these are actually going to be negative since we're losing distance. Alright, now what we want to know is we want to know how's this distance changing. So we want to know, well, what's z prime of t? What is that going to equal? So how we're going to figure this out is we need some way to relate all this information together. So how do we relate all of these derivatives or all of these functions together? I know we can use the Pythagorean theorem. So remember, the Pythagorean theorem is going to be y of t, or our y function, squared plus our x function squared equals our z function squared. Pythagorean theorem. Now, if I want to figure out z prime of t, what I need to do is I need to take the derivative of this whole thing. Now remember, when I take the derivative of this guy, I'm going to have to use the chain rule. The reason is that all of these are different functions, and all of these have the same outside function, which is that it's being squared, and then we're doing the inside function, which is over here y of t, x of t, and z of t. So let's go ahead and take the derivative of this guy. So using the chain rule, this is going to be, so the derivative of the outside, that's 2. Remember, we're going to leave the inside alone, so leave it as y of t. And don't forget, when you do the chain rule, you have to multiply by the derivative of the inside, so it's going to be y prime of t. Plus, do the same thing here, so the derivative of the outside, we bring the 2 down, leave the inside alone, times x prime of t. Remember, because the chain rule, leave the inside alone, then multiply by the derivative of the inside, equals 2 times z of t times z prime of t. Now, something kind of cool is that these all have 2's in front of them, so what I can do is I can cancel all of those 2's out. So now what I'm left with is y of t times y prime of t, x of t times x prime of t, and z of t times z prime of t. Well, I know what y of t is at the time I'm interested in. It's 225. So that's going to be 225 times, well, I know what y prime of t is. That's 150 plus x of t, well, that's 180. That's that distance right here, times x prime of t, that's, oh, I'm sorry, negative 120. This is also negative, equals z, which we figured out was 288.14, times, and we're trying to figure out what z prime of t is. So if we do all of the math on these guys, so if you multiply these out, add them to this multiplied out, and then divide by 288.14, what we're going to get is that z prime of t is going to be about negative 192.09 miles per hour. Now it's important that we have the negative there. The reason why is that that negative is telling us that as time moves forward, these planes are getting closer together. Now let's just stop. Does that make sense? Well, as this plane heads towards the airport and this plane heads towards the airport, doesn't it make sense that as they head towards the airport, that the distance between them would get smaller? Well, yes, it does. So, just as a little recap, when you're solving these problems, remember that anytime you see miles per hour or some sort of rate of change, that's going to tell you that that is the derivative. Also, don't forget to draw a picture first to kind of get your grounding and come up with some sort of equation that can relate all of your variables together. That's going to help you find an actual value for the derivative of interest.